All right. Good evening, everyone. So, hi, Tony. Hello, everybody. So this is our fourth lecture today and our last one before your first exam, which will be next Monday. So I am going to dedicate a bit of time Tuesday, the other Monday. Yeah, next Tuesday, the regular day of the week. So I'll spend a little bit of time and give you a chance to ask any of your questions about the exam, and then we'll get on to today's lecture, which is going to be a bit of a review of the last class, property and probability, and then I'm going to introduce your at least two of your three most important probability distributions for this course. So first, the exam, though. First thing is I've posted for you, you'll find on your left bar now something called practice exams, and I've posted there some practice questions for you and solutions for your first exam to help give you a better idea of what to expect and give you something to practice on. The exam next Tuesday is going to be for the whole class, so it will be from 5 p.m. till 7:50 p.m. I will aim to make the exam something that you're not feeling time pressure for, so that should be plenty of time to complete this exam. It's going to be an open book exam, which here means that you can bring any materials you want. You can use your own laptop, you can use printed materials, textbooks, you can use digital materials that you have on your computer, you can use the digital version of your textbook, you can access Blackboard and use anything that we've posted on Blackboard or any of your own notes. So it's a really open book exam. You can also use I'll give you for today, there's a Bayes rule calculator and a binomial distribution calculator so that you don't have to work through the formulas for these distributions. They're already there in spreadsheets for you. The only things that you can't do is communicate with anyone from the outside world. So you can't, you can't talk with other people via the internet or access other materials from the internet. You should only use what you bring with you to class. The exam will be administered via Blackboard, so I'll have you sign on to Blackboard. It will be there on your computer. You'll be able to move around. It'll be such that you can, even if you close down your browser and log in again, your exam will still be in progress. But once you start it, you'll have 2 hours and 50 minutes from the minute that you start. And it will cover everything that we've covered in the class so far, lectures 1 through 4, and materials from the labs and the assignments. Are there any questions about the exam? Yes.
Yes, I have 2 questions. First off, for the format of the exam, is it going to be pretty similar to like practice questions and stuff like that, or?
Yeah, the format, so it will be partly multiple choice, and it will be partly multiple choice, partly fill in the blank, like put in a numeric answer, and then possibly some essay type questions, where you put in like output from your analysis or something written. But it will be on Blackboard.
One more question.
Mm-hmm.
So in terms of if you have like next question, since for example binomial distribution, you can do it by hand. You can also use Excel. Would it matter if you use like a program by hand?
So you can use whatever software you want. Yeah, if there's a question about the binomial distribution, you can do it by hand. You can do it in Excel. You can do it with a calculator. However you want. And the questions won't be anything that would require you to do it any particular way. It's any way that you get to the answer is fine. You're welcome. Any other questions? Yes.
How challenging are the questions?
Yeah. So yeah, open book exams are a bit of a double-edged sword. It's nice being able to not have to memorize things, but it does like make it incumbent on me to come up with questions that will still challenge you. So I think, I don't know, you probably get an impression like from my lectures that I really try to convey a conceptual understanding of the material, and I will have some questions that are like that too, to try to test your conceptual understanding of it. There will also be some that are just, okay, here's another probability question, just do it again with different numbers. But I'll do my best to have some on there that are a little bit more challenging. If it turns out to be too hard, I will scale it, but I do want to have a chance to probe a little bit beyond the can you do the calculations. I don't know if that answers your question. Yep. It is what we did in the lectures. So yeah, if there are sections that are like from chapter 3 that are not in this lecture, I won't test you on them. Yeah. The lectures to me are the gold standard of what's covered in the course. Any other questions?
Any review?
Any review? I don't know, Tony. Are you planning to do a review session?
I'm gonna do something tomorrow night, and I'll do something also on either Saturday or Sunday morning. I'll post it online.
Okay, a couple of review sessions. Someone sent me an email asking if I could cover one of the examples from the lecture, and I'll do that too. Maybe I'll just screencast that and record it and post it before the exam. So yeah, you'll have your practice exams, you have your assignments, you have your lab materials, making sure that you understood the concepts from the lectures, and then some additional review sessions that you can use to prepare. I guess not to frighten you or anything, but I think you can expect the exam to be a bit more challenging than the assignments, just based on past semesters. Okay, any more questions? It's not your last chance. You can ask me later too if you think of something. All right, so just to review the stuff that we covered in the last class, I introduced you to properties of probability and their applications to diagnostic tests. So I'm just going to review some of these basic properties of probability. There's something called mutually exclusive events. Remember, an event is something that has a definite measurable outcome. And if two events cannot both occur, we call them mutually exclusive. And in this case, the probability, so one example would be having cancer or not having cancer. It has to be one or the other. Then the probability of having cancer or not having cancer, so these two mutually exclusive events, is just equal to the sum of those two probabilities. And in this case, since those options are exhaustive, they add up to 1. So in general, the sum of the probabilities of all possible events, so the exhaustive list of possible events always equals 1. And that's a property that you'll exploit when doing some probability calculations on these distributions that we'll cover later today. And on the other hand, the probability of them both happening, so of the probability of having cancer intersected with not having cancer is 0. You can't have both if they're mutually exclusive. So these two things are basic properties of any probabilities. If they're not exclusive, then in a Venn diagram there's some overlap. So in a Venn diagram, these circles represent the probability of events. So I'm representing with one circle your probability of having cancer, and then everything outside of that circle is the complement of that, not having cancer. And then with the second circle, I'm representing the event of having heart disease. And this overlap or intersection is telling you that there is some probability of both of these things happening. It is possible to have both cancer and heart disease. And you can relate these. So these are the union and the intersection again. The probability of the union of cancer and heart disease is the sum of the two independent things, like on the previous page. But we have to subtract off this area in the middle, which otherwise would be counted twice, because they're not mutually exclusive. If these are independent, that is, that your probability of cancer or heart disease is independent of having the other, then the probability of both is just the product. So the probability of having cancer and heart disease is just equal to the probability of having cancer times the probability of having heart disease. If they're each 1 in 100, then the probability of both is 1 in 10,000. If there's something that's each 1 in 3, then the probability of both is 1 in 9. That's only if they're independent of each other. So like separate coin flips in a fair coin, your probability of flipping heads on any given flip is independent of what happens the last time. Then you can just multiply these probabilities to build up the so-called joint probability of multiple things happening. And by corollary of this, if these are independent, then the probability of the intersection of 2 or 3 or 4 or any number of events is just the product of those probabilities. So the probability of any individual event, the probability of all of them happening is just the product of those individual probabilities. If they are not independent, we can use notation, this so-called conditional probability notation. So that is, if your probability of having cancer is different depending on whether you have heart disease or not, like a pre-existing condition, so, or it could also be, say, conditional on having a family history, conditional on having some risk factors, then instead of just being the product of these two things, it's the product of one of them. So I'm writing it this way: the probability of having heart disease times the probability of having cancer conditional on having heart disease. So I've just had to add this conditional aspect to the probability of having cancer. So instead of just the probability of cancer times the probability of heart disease, it's the probability of cancer conditional on having heart disease. There's another way that I could write this intersection, this probability of both. Can anyone tell me what that is? Almost the same as this, but a little bit different. What's another way that I could write this probability of having cancer and heart disease, besides the way I've written it here? So this is the probability of cancer conditional on having heart disease. What if I don't know that? What if instead I know the probability of having heart disease conditional on having cancer? How could I write this instead? Yeah?
Just flip it. P of H and then C.
If I can get my, oh, sorry, probability of, say that again?
Probability of P is H and then C.
Yeah. Given. All right, then what else do I have? What else do I put?
Multiply by the probability of having cancer.
Yeah, very good. Very good. So both of these things will give you the probability of having cancer and heart disease. And the right-hand side of these equations, it turns out, gives you Bayes' rule. All you have to do is take and did I see anything here? And divide them through either by probability of heart disease or take them and divide them through by probability of cancer, and it gives you Bayes' rule. So Bayes' rule is just a basic property of probability that tells you there are these two ways of writing the intersection. All right, here's your little cheat sheet again. These are all the notations that we learned. All right, so let's apply this stuff that you've learned now about probability to data. So I've been talking so far just about these sort of abstract probabilities, probability of having cancer, probability of these different things. But as soon as we're talking about data and we're talking about real public health outcomes, we're going to have to recognize these in the context of random distributions that we're going to start covering today. So first of all, definitions. A random variable is any characteristic that can be measured or categorized and where any particular outcome is at least partially determined by chance. So it can be partially predetermined, but it has to be at least partially determined by chance. Or it can be all determined by chance. Some examples could be the number of new diabetes cases in New York City in any given year. That's an example. Certainly part of it is predictable based on previous years. You could make like probably a pretty good estimate of how many cases there will be next year, but you can't predict it exactly because it's a fundamentally unpredictable thing, whether an individual is diagnosed with diabetes in any given year. So that was like a citywide variable. It could also be an individual, property of individuals, such as the weight of a randomly selected individual in New York. So again, that's something that just like, you know, if we know that they're an adult, we could probably look up from one of the New York City health surveys what the average weight of New Yorkers is, and probably also the standard deviation, and we could make an educated guess as to what it is that would be better than saying between 0 and infinity, but we can't know exactly what the weight of someone who we don't even know who it is yet. Is the lecture streaming in here?
Somebody's got a speaker on, not me. I think it's gone that way.
All right. And random variables come in in these three types. And these are the same types of data that I was talking about earlier in the first couple classes when we were talking about types of graphs and descriptive statistics. We have categorical random variables. That includes the nominal variables and ordinal variables. But they're categorical because they can only be in certain categories. Discrete random variables, these are the ones that are numerical, rules of math apply to them, but they're discrete, such as the number of children in a household, such as the number of visits to an emergency room, things that can only take certain discrete values. And then continuous random variables, where any value between certain bounds are allowable. As a matter of notation, I'm going to rate random variables using uppercase letters and particular realizations of those in lowercase letters. So for example, the distribution of individual body weights would be an uppercase letter, and any individual person's body weight would be a lowercase letter. And if it's for an individual, it would have some little subscript to identify which observation among many, if it were a study. All right, so this is very similar to the types of data that we discussed, but it's a little bit different now because I'm talking about distributions. I'm talking about random distributions rather than just about data and the realizations of those data that we talked about before. So before I made a plot of we have a pain study where people report mild, moderate, and severe pain. Here's how we can, that's a categorical variable. Here's how we can display those data as a frequency table or as a bar chart, things like this. These are the observations would be the same, but I'm not actually talking here about individual observations the way we were before. I'm talking about the probability of these observations. And so I'm talking about a random variable. So the Ladsteiner blood groups, the most common is O positive. The second most common is A positive. And these each have percentages associated with them according to, in the US population, the percentage of people who are of this blood type. So by specifying the possible values of this categorical variable and the probabilities of each of those values, I'm specifying here a random variable. I'm giving you its distribution. So without even telling you anything about, how many people, this isn't something that I don't have counts or anything like that. I just have this probability distribution. So what are each of, if we were to go and do a health study where we measure individuals' blood type, what would each of those, each time we got back a result and found out what someone's blood type was, what would that be in our probability terminology? It would be an event, right? Something with a measurable outcome and that we have measured. And all of these events together, are they exhaustive? Why not?
And then I'm just gonna say, because it's, again, probably less 4 pieces.
They are exhaustive because they add up to 100%. There are no other blood types in these anywhere in the world, not just in the US, but regardless, if the probability of the events that you have adds up to 100%, then they are exhaustive. So I've already told you this, but what kind of a random variable is this? Yeah.
So each blood type is the event, or each personal observation, each person that you do is?
So once we gather data and get back a result for a person, that is an event. Yeah.
But the exhaustive part is not related to the event.
No, that's right. The exhaustive part is a statement of the fact that these are the only possible events that we can observe. That the probability of each of these added up is equal to 100%.
So these are the only outcomes.
These are the only outcomes that are possible. You're welcome. So what kind of random variable is this? Categorical. Very good. All right, let's have another example. The number of visits to the obstetrician's office during an uncomplicated pregnancy. This is, yes?
Yes, what type of variable was the last example?
Categorical. Yeah. So this is something also presumably calculated from a large number of observations. We have a 20% chance of 0 visits, 20% chance of 1 visit, 50% chance of 2, and a 10% chance of 3 visits. So what kind of random variable is this? Discrete. Yeah, very good. It's discrete. And are these, well, I guess I'll say first, just given the distribution as listed here, are these values exhaustive? Yeah, as stated here, 50.5 plus 0.2 plus 0.2 plus 0.1 is 1, so they're exhaustive. I mean, in real life, that's, I doubt they're exhaustive. There's probably a long tail, but given the data that you have here, these possibilities are exhaustive. So just for example, once you know that if I gave you 3 out of 4 of these and told you they're exhaustive, you can calculate, you can fill in the blank, right? Because you know they have to add up to 1 or 100%. So yeah, it's discrete or discrete quantitative. All right, how about the distribution of BMI in a population? So individual body mass index, what kind of variable is this? Continuous, yeah. This is a continuous quantitative variable because it can take any value between the possible, between the limits. And you know, as I talked about it when we were talking about types of data before, I said, you know, there's, you know, measurements are always discrete, but as long as they're fine enough, it doesn't really matter. But when it comes to a random variable, this is, if we choose to represent this as a normal distribution, as we probably will, that is truly a continuous random distribution. In that any value, well, for a normal distribution, any value between minus infinity and infinity is possible. Might have very low probabilities, but any value is possible. So that's a continuous random variable. All right, let's talk about continuous random variables. We will represent these. You'll see a lot of visual representations of the probability distribution of a continuous random variable using curves like this. These curves are probability density curves, and they're just showing you the height is somehow proportional to the probability of an event at that particular time. But what's less important than the actual height is the area under this curve between two possible values along an interval. So for a probability curve like this is a probability density curve. What it is useful for is if you want to estimate the probability of an outcome that is between two limits, like this interval here. So the probability of a BMI between 20 and 27, let's say. You can use this curve to calculate what that probability of having an observation between those limits is. So here on the x-axis, these are the units of measurement for our variable. BMI is what is it? Centimeters per kilogram or something like this. In this case, it's time, and the y-axis is a probability, so it has no units. For any probability distribution like this, the total area under it is going to add to 1, because the probability of having some observation, assuming that there isn't a probability of just having missingness, like no observation, has to add up to 100%. So no matter what we're talking about, whether it's body mass index or weight or whatever other continuous measure, the probability of that being between minus infinity and infinity obviously has to be 100%. We could limit it more than that, but this distribution will tell us the probability of observing something between any given interval, and if we take those intervals all the way out, that probability has to be 100%. So we'll be interested in the area under intervals on these curves, and any interval will have a probability or an area somewhere between 0 and 1. The narrower the interval, the smaller it will be, the closer to 0 it will be. But it's an area, it's always positive, and it can never be more than 1, because for all exhaustive possibilities, the total probability is 1. So as I said, the interval containing all possible values has probability equal to 1. And the two most important probability distributions for this class, maybe there's a third one that's pretty close, but is the normal distribution for continuous outcomes. Well, I'll also introduce the t-distribution later, next class, I think it is. And for binary outcomes, it's the binomial distribution, and these are the two that I'm going to introduce today. So the normal distribution is a continuous distribution that is sort of bell-shaped. You'll see more about what that is, but it's an important distribution because it happens to fit a lot of different kinds of data. And the binomial distribution, anytime you have two possible outcomes and each of those observations or events is independent from each other, then the total number of times that event occurs will follow binomial probability distribution. So that is why that one is important. The normal distribution is symmetric about its peak. So what's to the right of the peak is exactly the same as what's to the left of the peak. It's bell-shaped, meaning it has a peak and it drops off and has these sort of, tails that get closer to 0. And it's characterized by just these two parameters, the mean, and the mean is where the center is, and the standard deviation, sigma, which determines how wide it is. So in these three examples, this tallest one is the one that has the smallest standard deviation. So this is a mean of 0 and sigma squared of 0.2. This wider one down here is also a mean of 0 because it's centered on 0, but a standard deviation squared of 1. So you increase sigma, you increase the width of it, and lower the height. And then we have another one with a mean of 0 and a sigma squared or variance of 5. That's the very wide, very low hill. And then we have an example here of a mean of -2. So you can see how these two variables, they shift the peak around and they make it a higher, steeper peak or a lower, shallower, flatter peak. Here's an example of the heights of men and women, where the height of women is being described as a normal distribution with a mean of 65 inches and a standard deviation of 3.5 inches. And the heights of men at a mean of 70 inches and standard deviation of 4. So there is the distribution for women. It's a bit over to the left and very slightly narrower, although not enough that you could really see in the plots. So within what interval do almost all of the men's heights fall? Probably between about 60 and 80. And women's heights between about 55 and 75. But there's a fairly substantial overlap in this range from like 60 to 75. The empirical rule is kind of a handy thing to know just for simplifying a lot of normal distribution calculations. And it's just a list of probabilities for intervals centered around the mean. So if you have an interval centered around the mean that goes to plus and minus a standard deviation, that contains about 68% of the probability. So the probability of an event in this range, let's say if that's whether it's a BMI or a weight, is about 0.68 for any normal distribution, as long as you're putting this interval at plus or minus 1 standard deviation centered on the mean. Plus or minus 2 standard deviations from the mean contains about 95% of the probability, and plus or minus 3 standard deviations contains about 99.7% of the probability. And those are just there's nothing special exactly about these intervals other than that they come up more frequently than others, and it can be kind of useful to remember this or to have it handy when you're answering questions, because if you're asked quickly, like, okay, here's a normally distributed variable, between what values would 95% of observations lie? You know, quickly it's plus or minus 2 standard deviations from the mean. So if you have the mean, you just subtract 2 standard deviations and add 2 standard deviations, and that's all you have to do to answer that question. So going back to that example of the heights of adult women with the mean of 65 inches and standard deviation of 3.5 inches, and applying this empirical rule, 68% of women in this population will have heights between 61.5 and 68.5 inches. That's just 65 plus or minus 3.5. 95% will be between 65 plus or minus 7 inches, and 99.7 will be between plus or minus 3, so 10.5 inches. So the symmetric calculations with the empirical rule are easiest, but what about asymmetric ones where you want the area to one side or the other all the way to the other end of the distribution? And in order to do this, you can either, like if it is somewhere with where you have a result from the empirical rule, you can use a calculation like this. So if I want the area, so say the probability of what proportion of women are less than 68.5 inches tall, that means I want the probability from +1 standard deviation all the way down to 0. One way I can do that, just if I were doing this sort of off the top of my head, would be to say, okay, well, between plus or minus 1 standard deviation, that's 68%. That leaves 32% in the 2 tails, 16% in each tail. So I'd take the 68% plus 16% and get 84% to do that, to answer that quickly. For this, or for sort of non-round numbers, you'll also be able to use a probability table or software for doing this calculation. So that was, we were kind of implicitly using what is called the standard normal distribution. So there's any number of different normal distributions. They have those 2 parameters. There's only one standard normal distribution, and it has a mean of 0 and a standard deviation of 1. So when you hear the standard normal distribution, that's what it is. You can convert any other normal distribution to the standard normal distribution just by subtracting the mean and then dividing by the standard deviation. So by doing that, you convert another normally distributed variable into one that has the standard normal distribution. And when you apply that to some other data or measurements, you call those z-scores. That process of subtracting the mean and dividing by the standard deviation. Or z-score if you're from Canada. For my first few years, I still called them z-scores, but I've been converted now. So here's a normal distribution of heart rates. Here's the same distribution, but standardized. What do you notice about it? What's that? Yeah, z-score. That's different.
And
These values are different. What's the same?
shape.
Yep, it looks exactly the same. All that is different is the scale. So we've changed the scale from being one of heart rate to a scale of z-scores. So no matter what the scale was beforehand, this is the scale of the standard normal distribution. But the distribution looks the same. It's still, normal distribution is a normal distribution in terms of the shape. The reason I'm telling you about z-scores is it makes it easier to compute probabilities using using a lookup table, and it's also sort of an alternative way of describing an observation in terms of its relationship to the distribution instead of in terms of the measurement. There is a table in your textbook, Appendix B1, called the normal probability table, and it gives areas in this left tail, and it has these nice graphics in that rather than just telling you these are left tail probabilities, it gives you a little picture showing you what the area is that it's giving you in the table. So for negative values of z, it looks like this. It's something, can you tell me something about what this probability is? What it's between? What's it more than? Sorry? I don't know if it's more than 25% or not. There is one number that I can be absolutely sure it's greater than 0. It's absolutely definitely greater than 0. What is it absolutely definitely less than?
50.
Yeah, it's both of those are right. It is absolutely definitely less than 1, and this one is absolutely definitely also less than 0.5, even though I haven't given you any numbers here. How about here? This is absolutely definitely greater than, yep, it is greater than 50% and absolutely definitely less than 1. You guys are great. And this is giving you a little bit of a hint to the answer of the question of, well, what do I do if I want the area under this right tail, not this left tail that it's giving me in the table? How can I get that? Yeah, I can go 1 minus this left tail probability will give me the right tail probability. So if you were using this table to find the probability that a normal random variable takes a value less than 1.43 standard deviations above mu. This is too small for me to see. Let's see if I can zoom in a little bit. So here's 1.4, 1.41, 1.42, 1.43. So that says 0.9236. So the answer to this question is 0.9236. How about the probability that it takes a value greater than 1.43 standard deviations above the mean? Well, we can just go 1 minus that previous answer, which is so 1 minus 0.9236 is 0.0764. These are just here for your convenience. A few important z values. Out of these, one of them is far more important to you than the other 4, and that is this one. This is one that you should know well by the end of this course. That the oh, wait a minute, that's right. Yeah, that the probability of z being greater than 1.96 is 0.025. Anyone want to guess why that one is important? Sorry? No, it's not quartile 1. It's 2.5%, not 25%. Well, if the probability of z being greater than 1.96 is 0.025, that's just one tail, then the probability of both tails, so z greater than 1.96 or less than negative 1.96 is 0.05. And people like probabilities of 0.05 in statistics. And they also like probabilities of 95%. We'll be working with those particular values a lot. But that's why this is an important z value, 1.96. I also want to mention that you are also perfectly free to use this norm.dist function in Excel instead of bothering with the lookup tables. You can get all of these answers using the norm.dist function, and it has options for upper tail or lower, right tail or left tail. There's also one in R called I believe it's pnorm that does the same thing. So maybe you like using tables, they work perfectly well, but if you prefer using software, it also works. Ready for time. Oh, we're okay for time. Okay, so another example here. Find the probability that a normal random variable assumes a value within 1.43 standard deviations of mu. So before we had, well, oh no, different question. So let's see. Going back to here, this was we were just looking under the whole left tail here, and that answer was 0.9236. So here, for this one, we don't want, in the last question, it was everything to the left of here. Now I want everything to the left, but minus this tail. So one way to do it is to take this total area to the left of 1.43 and subtract the amount to the left of minus 1.43, since our table provides probabilities to the left of a particular value. And then it's 0.9236, the value we had before, minus 0.0764, which was the other value we had. We calculated it for the right tail, but it's the same for the left tail to give us this answer of 0.8472. An alternative calculation would be to directly calculate this area to the left of minus 1.43, which is 0.0764, double it to get the two tails, and then subtract it from 1 to get what's in the middle instead of in the tails. So if you're using the tables, you have to be kind of comfortable with these rules of symmetry and of the entire area summing up to 1. If you're using the software, probably you will just, for any interval, take the left probability of the upper value minus the left tail probability of the lower interval and just do it the same way every time. But regardless of how you do it, if you're given a probability problem like that, what is the probability of having a height between this and this interval? I recommend just drawing it out and putting those intervals and shading it in so that you're clearer with yourself about how to calculate the probability you're being asked for. I think it's very helpful to draw this out as a way of avoiding making mistakes. You'll get more practice of this in the lab. So these were examples of I've given you the value of z and asked you to calculate the probability in a certain interval. You can do the reverse as well, where I ask you for a certain cumulative probability and ask you what the value of z is, or alternatively what, say, the height is, instead of just the value of z. You can do this again using the body of that table, and you can do it again also using Excel. This is probably going to be asked either for some symmetric area about the middle or for like a left tail or a right tail as opposed to some arbitrary interval among here. But it's again using that table, but you're instead of looking up there was like one, the first decimal place along the top and the second decimal place along the side, you just look for the value to find the z-score. And in software, this is called the quantile function. So it's in R, it's called Q-norm. I think it's I can't remember what it is in Excel. It might still be norm.dist, except with an argument for quantile. So for example, the value of z for a cumulative probability of 0.025, this is talking about here in the tails. You would have to, if you looked up the left tail probability, you would find it at 0.025. So if I were to go back to here, let's see. This is the positive z table, so I'd have to look for 0.975, and I didn't go down. I didn't get up to 1.96, so we can't find it. But if I followed further down this column, eventually I would see 0.975, and it would be at 1.96. All right, so this is just for your own assistance in tackling these problems in a systematic way. First, stating the problem in terms of the random variable and the realization of it. So for example, the probability that my random variable uppercase x takes a value less than this particular realization lowercase x. Step 2, standardizing x to restate the problem in terms of the standard normal variable. So turning that into, instead of big X lower than small x, the probability of z, the standard normal distribution, being less than this particular z-score. Drawing a picture so that you know which interval you're calculating and whether there's some symmetry you can take advantage of, and then finally calculating that area using the lookup table or software. Okay, we're not done yet. But the binomial distribution, the good news is it's just another yes.
Sorry, are these slides online?
Yep, they're under today's lecture.
I don't see them there.
I downloaded them from the lecture, so they should be, unless I somehow didn't make them available. But let's see.
It's on the very bottom. Is it on the YouTube?
Oh, the recording?
So if you go to, here's our class, you go to weekly materials, session 4, February 26th. Go down to session 4 lecture materials, and there they are. Has anyone else been able to find them? You found them?
That one was empty, but it's all the way in the bottom of the YouTube one.
Oh, wait a minute. Oh, this item is hidden from students. Ah, sorry about that.
Follow that.
Whoops.
Sorry,
I didn't mean to hide. I didn't mean to hide them from you. How about now?
Yeah.
Is there now? Okay. Thanks for pointing that out to me. Is there anything else that's missing?
You know, you guys, happens all the time. You see the screen go blank and it's behind us, or if you see something disappears from Blackboard, tell us in the beginning, not after an hour.
I just thought it was me.
We're not mind readers.
Yeah. No, thank you.
See, I also have Levi's view of it, so to me it looks like it's there also.
What's that?
The student view is different than, our instructor view is different than yours.
Yeah.
So to me and Levi,
To me, there's just this little hint there saying this is hidden from students, which I might not notice. Session 1 you can't see either? Let's see. Session 1.
Why don't you go ahead and work? Go ahead.
Okay. Oh yeah, look at that.
I'll take a look at session.
Okay. While I'm here, I might as well just click yes. Okay. If there's any more, I'll fix them after class.
Session 1 should be ready.
All right, so before you get scared about this equation, I'll tell you, you don't actually need it. I didn't even show you the probability density function for the normal distribution. I don't know why I show it here, just, I don't know, for the formula-minded people, so that you know that there's nothing magical about this distribution. What's important is that you know the conditions under which it applies. It applies to what is called a Bernoulli trial, which is one where we have a series of events, each of which has 2 possible outcomes, and we call these either a success or a failure, even though it might not be obvious which is a success and which is a failure, such as with a coin flip. You still just choose one of them to be your success as a matter of terminology. So each of these trials or each of these events has to have 2 possible outcomes. Each of them has to have the same probability of success, and each has to be independent. And as long as those 3 things hold, then the probability of X successes in N trials, where each has the same probability of success P, is given by this. And this is the binomial distribution. So like a normal distribution, it also has two parameters that define it, except it's this number, the number of trials and this probability of success in each one. And sort of like the mean and the standard deviation, the number, well, except they both of them determine where the center and what the spread is. In this example here, here's 20 events with a probability of success in each one of 0.5. The peak then is at 10. If we have 100 events, each with a probability of success of 0.5, then the center, the most probable number of successes is 50. The probability of, if we have 100 events and 0.3 probability of success, then the most likely number of successes is 30. So where the center of it is fairly intuitive. It's just the number of events times the probability of success in each one. Like if you flip a coin 100 times, the most probable number of heads is 50. If you roll a dice 10 times and all you care about is whether it's a 1 or not, then your most likely number of ones is 100 divided by 6. So as an example, if the prevalence of diabetes in an elderly population is 10%, what is the probability that if you randomly select 4 individuals from this population, that exactly 3 of them will be diabetic? So this is a Bernoulli trial with n equals 4 and a probability of, we'll call having diabetes a success. So probability of a success in this trial is 10%. It works out to 0.0036. And we could calculate this for 0, 1, 2, 3, or 4. Those would all have non-zero probabilities. Alternatively, how about what is the probability that at most one of those 4 individuals will be diabetic? So that is the probability of 0 diabetics, which turns out to be 0.65, plus the probability of 1 out of 4 diabetics, which is 0.29. And that probability is almost 95%. So you can just add these like the union as we did before, because they are exclusive events. There has to be either 0 or 1 or 2 or 3 or 4 diabetics in a group of 4. All right, how about in this group of 4, the probability that at least 2 of them will be diabetic? The easiest way to do that will be to just do 1 minus the probability that you calculated on the previous page. Otherwise, you could do probability of 3 plus probability of 4 plus probability of 2. And again, there's a function in Excel that you can use that would probably be helpful to get comfortable with. It's this binom.dist function. As it turns out, for relatively large numbers, this binomial distribution approximates a normal distribution with mean of the number of trials times the probability of success and a standard deviation of n times p times 1 minus p. And if you have relatively large numbers, like you're talking about 1,000 individuals from this elderly population instead of just 4, this turns out to be more practical to do than using an exact calculation, because those factorials get very large. So you can use this. So in this example, 1,000 individuals, we expect about, let's see, 0.1. Wait, this is wrong. Somebody tell me what's the right answer here. Prevalence of diabetes equal to 0.1. Yep.
Should it be 0.00? Is there a 0 missing?
Well, if it were a prevalence of 0.01, then this would be correct. One or the other is wrong. Either the prevalence is wrong or this calculation of the expected number is wrong. I'm going to assume that it's this calculation that's wrong because we used the prevalence of 10% on the previous couple slides.
So just to double check, it would be 0.01?
No, 0.1 for a prevalence of 0.1.
Okay.
That's the same thing as a prevalence of 10%. 0.01 would be a prevalence of 1%.
Okay.
So just as a sort of rule of thumb, if both, this is your expected number of successes and your expected number of failures, if those are at least 15, then this approximation is going to be very good. All right, so just to wrap up, you should know your probability notation and get a fair bit of practice with just doing basic calculations based on those rules of probability. Calculations based on knowing that the sum of probabilities of exhaustive events is equal to 1. And the other things that that you learned, adding, multiplying probabilities. And we will be using this normal distribution, binomial distribution, and the normal approximation to the binomial distribution for a fair bit of other things later in the course. Our new notation for today was a capital Roman letter for a random distribution, lowercase, corresponding lowercase for a realization of that random distribution, n for a number of observations, p for probability, mu for the mean of a normal distribution, sigma for the standard deviation of a normal distribution, and capital Z for what? Capital Z is the standard normal distribution. The lowercase z would be a z-score. You will have to know how to do probability calculations and lookups for these two distributions, the binomial and the normal distribution, for both upper and lower tails and middles of the distribution. All right, and with that, are there any other questions before I'll give you a bit of a break and we'll move on to the lab. All right, thank you.